Every time electricity moves from a power plant to your home, a significant portion of that energy simply vanishes before it reaches the plug. This happens because of how electrons behave in standard materials. In a copper wire, moving electrons act like a disorganized traffic jam, constantly colliding with the wire's atoms and microscopic impurities. Each collision converts a small amount of that electrical energy into heat, which then radiates away into the environment. This opposition to flow is known as electrical resistance. It acts as a permanent bottleneck, ensuring that every electronic device and power grid on the planet operates with a mandatory level of waste. In 1911, Dutch physicist Heike Kamerlingh-Onnes discovered a way to bypass this friction. While cooling mercury to extreme sub-zero temperatures, he recorded a state of matter that shouldn't have been possible. When the mercury reached its critical temperature, electrical resistance didn't just fade, it ceased to exist entirely. Once a material becomes superconducting, it carries current with zero loss, flowing indefinitely without any external power source. This discovery proved that the laws of electrical friction aren't universal. They are a condition that can be turned off if the environment is right. To understand why this happens, we have to look at the subatomic level as temperatures approach absolute zero. Normally, electrons repel each other, but inside a freezing metallic lattice, they form Cooper pairs, overcoming their natural repulsion to move as a single unit. These pairs become a single coordinated wave, gliding perfectly through gaps in the atomic lattice without hitting a single atom. By synchronizing their movement into this quantum state, the electrons remove the physical opportunity for collisions, effectively eliminating the source of heat and resistance. Beyond zero resistance, superconductors also exhibit the Meissner effect. This is a phenomenon where the material completely expels magnetic fields from its interior. This magnetic expulsion creates enough force to allow a magnet to hover in place, providing a form of stable levitation that is completely free of physical friction. We already use this property in the medical field. Inside this MRI machine is a series of superconducting magnets that produce the stable, high-intensity fields required to create detailed images of human tissue. In transit, this same levitation effect allows maglev trains to float above air tracks. By removing physical contact, these vehicles can reach speeds exceeding 500 kilometers per hour because they are no longer fighting the friction of the rail. These technologies are only possible because we found a way to apply the rules of quantum physics to large-scale engineering. However, there is a massive engineering hurdle. Maintaining this state requires cooling systems that use liquid nitrogen or helium, which are expensive, volatile, and difficult to maintain. This 3D radar chart shows the safe zone for superconductivity. If the material gets too warm, or the magnetic field or current gets too high, the effect vanishes. In 1986, researchers discovered ceramic materials that remain superconducting at much higher temperatures, expanding this zone. Yet, because these boundaries are still so narrow, this technology remains confined to specialized facilities rather than the standard wiring in our homes. Today, the primary focus for researchers is the search for a material that can maintain this resistance-free state at room temperature. Success would mean a complete overhaul of our energy infrastructure, as we could transmit power from remote wind or solar farms across entire continents with zero energy loss. Combining zero-loss power grids with frictionless high-speed transport would effectively eliminate the thermal waste that has drained energy from our systems for a century. Breaking the thermal barrier isn't just a technical improvement. It would remove the inherent energy tax that has limited human engineering since the dawn of the industrial age.